afternoon, good morning, good afternoon, good evening, depending on from where you join. So it's amazing that so many of you can join today from all around the globe. And I think we have a wonderful lineup today of speakers to discuss workflow orchestration for self-driving labs from various angles. So yeah, great that so many of you could join. And it's obviously not the first time we discuss workflow orchestration. So last year at Accelerate, oh, Alan is also here. That's great. So last year at Accelerate, we also organized a small workshop around workflow orchestration. And one of the things we asked the participants of this workshop was like, what associations come to mind when you hear workflow orchestration? As we realized throughout the years in all these good discussions around workflow orchestration, everyone thinks about slightly different aspects. So for some people, it is mainly about device integration in the lab. For other people, it is the entire self-driving workflow loop, so including also the experiment planning. So we were just curious what people think it is about. And yeah, here we see a bunch of answers we got. Since Accelerate is dedicated to self-driving labs, it's not a big surprise that closing the loop came up most frequently. So people are really then already concerned about closing the loop between the lab and their experiment planning, including everything that has to do with data management, data orchestration, so capturing data in the lab from the robotic systems, and then feeding them ultimately to an experiment planning framework to start over again. A lot of people mentioned also integration challenges, which probably also doesn't come as a surprise for many people here in the audience. And some also already mentioned things like agents, which are obviously already quite popular nowadays. And they should then also be used for planning and other aspects for the orchestration. The other thing which came up frequently during this meeting and also during Accelerate itself was the question, why are there so many of these orchestrators? Aren't we actually all doing the same thing? Aren't we reinventing the wheel over and over again? Isn't it time to align these efforts to team up? And that's basically how this meeting also came to life, that a bunch of people, which we showed on the title slide, came together, organized this event. And just to give you an idea how many there's out there, and this list is probably not even complete. So a lot of orchestration systems have been developed over the years, not all of them obviously for self-driving labs per se, but some of them were mainly focused maybe on the computational aspect of things. But a lot of them are actually dedicated to self-driving labs. And this list, as mentioned, is not even complete. So here we focus on the non-commercial solutions that have been published or will be published soon, that already have a name. There are probably many more out there where people locally developed solutions that work for them. Again, not all of them for self-driving labs. They have been developed for different domains, for different use cases. But the challenges these systems face are quite comparable. And so and also if you develop your own system, which you would like to publish, which is not shown here, please let us know. We want to make all these overviews available at some point on a website, not only for orchestration, but also for self-driving labs in general. So something like a cookbook for self-driving labs. And then orchestration is obviously a very important aspect of the game. So please get in touch. And then for this meeting today, what we would like to discuss are three different elements. So one of them will be challenges and expectations around workflow orchestration. So we will hear from end users about application areas that require workflow orchestration, what an ideal orchestrator would look like or from their perspective, and also which impact it would create. So what would an ideal orchestration system allow them to do, they currently can't do. So that's one element. The other element is, as already mentioned, to look at the existing landscape. So out of these orchestrators we've seen on the previous slide, we will hear about 7 of them, mainly like the background, so why it was developed, what success criteria exist for it, and also then how end users would interact with the system. And yeah, something about architecture features that the system provides. So that is hopefully very educational for everyone. So to see a bit what's already out there. So even at Accelerate, where the community is of course quite into this orchestration part, I think a lot of us learned about completely new systems we were unaware of. So in this meeting also provides now a bit more background in this regard. And then in the last part of the event, we would like to get your input. So from the entire audience, about challenges you face, about priorities you would have around workflow orchestration, so that we can, after this meeting, then really start defining a roadmap towards then a community-driven orchestration system. So it might be a similar setup as we see for operating systems. Decades ago, there were a lot of operating systems out there. Nowadays, we converge to a handful. And a similar thing we could imagine for orchestration systems for self-driving labs. We start off with a lot of them, and we converge to a few of them. So this earlier discussion, like, aren't we all doing the same thing? These discussions got even a bit emotional. So some people felt like we are wasting resources. We should use the few hands we have in a better way. And others saw it more positively and say, well, it's too early to align on everything. We're still experimenting what these systems should do. And we should look at it from a more positive angle and say, well, we try to solve similar problems with different approaches. So as a community, we now learn what works, what doesn't work. And now it's time to align. So now we learned a lot and can move forward. So out of this meeting, ideally, we learn a bit more, which problems are we actually solving, and how do we know that we are successful? So if that is what we get out of this workshop today, that would be wonderful. And then based on it, we can define the roadmap. If you want to get involved as someone who would like to develop such a system, provide feedback from an end user perspective, like what should be in there, or evaluate prototypes, or as a sponsor, please reach out. So everything is welcome in this regard. And yeah, we have 11 speakers today for this first part, end user challenges and expectations, 4 from 4 different big corporations. We take a short break after those presentations and then dive into these 7 examples of non-commercial orchestrators and take another short break and then gather your input. The presentations will be chaired by Sergio. So he will take over then from here and hopefully has less technical challenges than I had when I started. And the closing remarks will be done by Noah, who will also present actually one of his tools. And yeah, now I wish everyone a nice event. Look forward to all the discussions we might have in the chat. And yeah, enjoy. So Kalpesh, you can go ahead, share your screen. And yeah, have a nice event, everyone.
Hello, everyone. Just checking, can people hear me?
Yes, loud and clear.
Thank you. Perfect. Thank you. Okay, so I'll start. So thanks a lot, Will and other colleagues to arrange this, and thanks for inviting me to talk about this. Today, I'm going to talk a little bit about workflow orchestration and what I think. In my opinion, it's a runtime layer that closes the gap between planning and scheduling. Also, all what I'm going to talk is just a conceptual idea and does not include anything confidential. With that, the first thing which I want to talk about is a difference between scheduling, planning, and orchestration. When I talk to people, it seems that a lot of people use these terms in a slightly different way and interchangeably. So I'm going to talk a little bit about what I think. In my mind, it goes planning. Planning is how this whole thing will work in days and weeks, and what and how things will happen. And the output is we make a plan and assume. In scheduling, we comes as the things which need to happen in hours or days, and where it will happen and when. And the output comes as run list. And then orchestration, which is the real time. It mainly answers the question what happens next, and it helps us to troubleshoot on the spot. So in my mind, it goes from plan to schedule to the orchestration. Now, talking about a little bit of a use case. So I'm going to take these two different ends of the use case. One is on the research side, which is DBLT, design, build, test, learn, where we plan an experiment, we execute, we measure the data, and based on that, we learn. And then we do the loop over and over again. On the right side, I'm going to talk a little bit about end-to-end journey of manufacturing, where you intake a material, you make the final product, you QC it, and you release it. Some of the common failure points in my mind is manual hands-off, or finding where is the material or what is the status of it and when it will be ready for next steps. The other important thing is data, metadata lost between tools, because again, people are using different tools, different LIMS, ELM, and it's hard to keep all the data together. And then the scheduling. Scheduling is very brittle, and it's really hard to recover from a failure or any recovery. Now, with that, the next thing I'm going to talk is what is an orchestration in my mind. An orchestration is a coordination between human, machine, software as one workflow. To me, it's not just working on machines or software. It needs to involve all three components to become a perfect loop. Then it's dependent, and it can maintain the resource constraints which come in place. And the other most important is recovers. As I was mentioning, it can recover by itself or easily, and that recovery can be either it pause, it retry, it reroute or resume. On the other hand, to be very clear, what is not an orchestration? Orchestration is not a scheduler. It's not a replacement for ELN, LIMS, MES. Those are different. It's not just one-off integration project where you created a project, you did an orchestration, and it's done. That's not orchestration. And the other thing is it's not a monitoring dashboard. It is not just there to monitor your equipment or experiment. It needs to have involvement with managing maintaining. As you can see in the diagram here, workflow and definitions come into the orchestration engine. It produces an event and provisions, and it connects to instruments, robot, ELN, LIMS, human, and it also monitors. So it's not just one of these, it's a combination of all of those. Going from here to what in my mind is broken in orchestration right now. And some of these things will be a little bit repeat from where I was telling earlier. It's not just a bespoke integration where you have some adapters and some scripts and vendors do some things where it's hard to manage or maintain. It's not just a siloed data. The results need to, right now results arrive late or out of context, and which is hard for reproducibility or AI loops. As I was talking about workflow, as we all know, in science, the workflows changes, and they changes very drastically. So we want the orchestration to help us to iterate them faster, not slow. Right now, the iterations on orchestrations are very slow. Recovery. Right now, most of the time when anything fails, orchestration just stalls and require continuous supervision of human, which lost throughput and trust, and you cannot run it overnight or over weekends. And then on top, last and most important is scaling. As we scale our orchestration, it need to work on multi-sites, permission, it need to be validated, it have signature and all those things, which right now cost a lot of money and a lot of rework for every time. So those are the things which I think are the important things which we as a community should work to fix. With that, now let's go back to my use cases. So if we take my first use case, which is self-driving lab, where we plan, execute, measure, and learn. In this, what it should support is it should support retries and reroute. At every step, it need to know if it fails, what need to happen, or it thinks and rewrite it. Metadata. Every data we get, metadata is more important or equal important to the data, because if you don't have metadata on what happened, where, which instrument, it's hard. And then it need to adapt based on the decisions which it made in the real time. Now, how we will tell that our orchestration was good? If the cycle time comes down, more importantly, the unattended percentage of the run need to increase, and model update time need to decrease. On the other side of the individual manufacturing, where we do samples, it need to follow the strict sequencing, because this is the actual samples and the sequencing matter. If there is a deviation, it can handle it. At the same time, it can record it for traceability. Now, in this case, the outcome will be a little bit different, because in this, time need to increase, deviations need to decrease, and turnaround need to decrease, because this is on a timely manner manufacturing and it need to meet the timeline. Now, to achieve this, what is that capability stack? And I will go from bottom to top. So bottom, it will be foundation first, then intelligence nest, last enterprise always. So what foundation means? So in the foundation, it means it need to have a universal integrations. It can connect to any software, any hardware. It's easy for humans to interact or enter data if needed. It need to be resilient. It need to have easy retries or reroute, and then data need to be there. Once we say, okay, we made the foundation, it works. Then the next come is intelligence, which is what we all talk about, AI and closed loop. So at that point, we introduce the closed loop AI hacks. We do adaptive selection. And now at this point, we put safety rails for decision, because when you are putting AI rules, you need to put the safety. And on top of that, once we have that, then we go to enterprise, where it need audits, it need e-signatures, it need metadata, and then it need self-serving service to make sure it's working as expected. Now, here is my recommendation for our MVP. The first phase is we make libraries and integrate libraries to everywhere. We make sure it's recovered easily. It can do data and provenance, and it's a self-service edits. Once that happens, then we prove it end to end. We pick one workflow which is high pain and high value. We run it reliably, unattended, at least several times to make sure it's running. We capture everything, and it is easy to change as science change. After that, we do the closed loop and compliance. So once we make the MVP, how we will say that it's a success or not? If we are successful, cycle time should decrease versus baseline. Uptime, unattended runs should increase. Recovery, it should auto-resolve the failures or time to recover should decrease. Data quality, as I said, metadata need to be there. Agility, the workflow can change quickly and we don't need to submit tickets. And compliance, it need to have audit readiness, evidence, and less deviations. And with that, here is a quick checklist that if we have to do and we talk about pressure testing or build versus buy, these are the things which we should look into. Integration, workflow engine, data and prevents, human in loop, security, and operability. With this, I would like to thank Will and everyone to attend this. And I'm happy to take any questions on chat or online.
Yeah, thank you, Kalpesh. Just to say that this meeting is being recorded for everyone in the chat. This is why we just mentioned that you need to turn off the cameras. All the speakers agreed with that. And yeah, after this, just like announcement, we can just start with the next speaker, that it's Martin Fitzner from Merck Group. So Martin, you can turn on the camera and then you can just share your screen.
Will do many things. I will just say, if something does not work, if you do not hear me, for instance, or do not see my slides, please say something. Otherwise, I will continue assuming everything is great. So thank you again, also from my side, for bringing the community together. I'm certainly looking forward to what we will discuss in the later stages. I will give a brief, share some experiences or expectations from an industrial viewpoint. And I have to start, of course, with one of our all-time corporate, little bit of specifications. In every talk, actually, there's two companies that go by the name Merck. And since this is organized by you guys sitting in Canada, I actually should be specific about this. In Canada, the company called Merck and Canada and US is not the same as it's called everywhere else in the world. So we hold the name everywhere except Canada and US. And, I don't want to bore people with the corporate thing, so I'll jump right into thing that is actually more relevant to the topic that I'm going to discuss. It's our company has not just one sector. It's not just a healthcare company, but actually Merck in Darmstadt, Germany has several sectors of business. And this is actually, we have beyond healthcare also life science and electronics. And as you can probably imagine, this translates into a lot of different requirements regarding orchestration and experimental design. So I brought here some bullet points that describe the subsectors a bit, where I see some differences. So healthcare, of course, has more bioassays and tox platform ADME experiments and needs to be heavily in a GMP environment. On the other hand, you have things like electronics, where we talk about entire buildings or pilot plants. And actually what people do there is more like processes, film design, materials science. So it's less chemistry, it's more materials design. And the analytics are also very, very different. It's essentially semiconductor materials. So as a result from that, the requirements that we have for plug-and-play orchestration are very difficult and super heterogeneous. And I want to give two examples, not necessarily for the heterogeneity of use cases, but also for the different scales. So this was our very first successful pilot, like orchestration use case, if you will. It's a super simple flow chemistry platform that was done already several years ago, just to prove you can have a fully closed loop system. A reaction optimizes itself without human intervention. And this is something that works on this little platform here. It does look very unspectacular, but it is essentially one vendor equipment, and you could control it via an API. And so it needed just two people, the experimentalist and somebody for the coding and the orchestration. And then you could make this platform, turn it into a self-driving lab. And on the other scale, we have aspirations like this. So this is our AI and drug discovery lab that is being built. It is essentially multi-room, multi-building endeavor, where we aim to have largely autonomous reaction discovery, reaction performance, and 100 different assays, so thousands per week. And ideally also with minimal human intervention. So this is like the end goal. And what we have here, of course, is we have many equipment vendors. As I said, 100 different assays. So the analytics are manifold, and it needs many, many more people. And probably it's this process of years. So just as examples of where orchestration is helpful, and I also want to make the point that, orchestration is not just helpful at this scale. It is also useful in smaller labs where we work with equipment that is not specifically bought, rebought, or entire rooms fitted. It is useful in labs that exist, and we also want to automate those labs where orchestration is needed. So here, quick perspective on components that I consider part of this orchestration thing. Of course, I used to think about only the right part as orchestration, but as you just work with it, you realize it's much bigger. So it also contains, in my view, the decision making and where to store and handle the data. So I just want to zoom in on the central thing a little bit, because actually I think the central part here is the one that's mostly solved. And there's off-the-shelf solutions that can handle the decision-making, the design process, if you want to achieve this kind of autonomy, or at least the support of the experimental planning process. And at Merck, we have our own solution for this. It is this Bayesian backend. It's actually free on GitHub. It's open source. You could use it there. I just show here the tech stack that we deploy internally for it. So there's this Python package on that. We build a REST API, which can be called from any piece of equipment or small PC, no computation needed. And on top of that is a graphical UI, which of course is really important for users who want to perform their experimental planning. So this I consider is kind of soft. I still have some pain points here in the center, especially a big thing that we keep fighting is you are reluctant to really enable your machines to run fully autonomously. And people want to have human in the loop, or at least human hypotheses. So these are things we're working on, but overall, on the grand scheme of things, I would say this aspect here is far progressed. So what I actually notice often is on the very left and on the very right, we have a lot of problems. So for instance, in a big corporate world, you even have a super heterogeneous data-based landscape. So there's not even one electronic lab notebook. There's different instances of the same company, and then there are different companies. And it is even worse on the right part, where we have, of course, labs that use a huge amount of different equipment. So actually my pain point, this is also how I got into this topic, is I work on this machine learning part in center, but eventually I want to bring it to people. They have some data and they want to connect it to the equipment. My pain point are always these little errors, the interfaces between, how can I now bring my decisions to the lab? And that's of course where orchestration ideally is easy, but in reality for me currently it isn't. I think here maybe agents are an interesting starting point, because if you have 100 different standards and you need experts who understand all of them and implement then these arrow connections, this is maybe more straightforward with agents who can learn from big specification documents. So just to make that point, I want to highlight some development we do in Merck in terms of a standard. So Merck has actually partnered up with Siemens very recently, but also before that we work on something that we use in our modular plants, and there's a standard called MTP. I'm not so sure, I don't think it's super aimed at labs and self-driving labs, but it is aimed at these modular plants. And for that, actually it's a super similar use case, but I think the kind of experimentalists in these two areas are not necessarily overlapping. But it is a standard that you can use, and it comes with a graphical user interface like the one you see here, where you can simply drag and drop and connect your equipment, and then you have continuous run through these connections, and the system can act and measure. And some special thing that we like to bring in, and we're working on that currently, is put the decision maker into here. So our Bayesian algorithm will be one of these boxes. You can configure it, and then you can connect it to the measurements, but also to set up the equipment in terms of the parameters. The goal is to have this fully plug and play, which is one of my big requirements actually for people using it. But this will come actually on this slide. I'm already nearing the end. So Willy has asked for a wish list, and here is my wish list. So I think I have a couple of I think it's 5 categories. And again, the least important one is probably the decision-making one. I think there's great algorithms for discrete design problems. When they are nested, you use maybe reinforcement learning, otherwise Bayesian optimization. I'm not so sure what's the state of the art for continuous optimization, not continuous spaces, but in our these modular plants, people would have continuous processes. It's not necessarily a match for batch-wise optimization. Of course, sometimes you can batchify, but At least I would see what is the emerging algorithm for that. For the decision making, I think interesting aspects are simulation in the loop, and which is related to multi-fidelity. So saving really a huge amount of experiments by doing a cheap surrogate measurement in the computer, essentially via simulation. How to smartly implement that is still to do for us. Compliance, I already heard also in the previous presentation, audit trails need to be kind of decoupled from devices. They need to be in a central place. Then of course data integrity, and for our regulatory colleagues, they always demand SOPs, statement of procedures, and they're ideal. We have reusable pipelines for validation, so it's not a huge effort each time again. Now, to me, a big topic is standards, and how can we actually, this situation is not sure if it's how easily it is solved, but what's really a problem is the heterogeneous landscape of the equipment vendors and standards they use. So the OPC UA is the standard for communication, but we need better or less APIs or unified API that exposes this. Similar for the capability model that would aid in autonomous discovery of devices in your potentially building in a room where you don't even sit. Like, this would be very nice. And for someone like me, I would wish for something where I can easily work virtually in a sandbox environment, because I'm trying to see whether my optimization algorithm works, and I can't always do that in a fully operational lab. So sandbox virtual environment would be great. Scheduling is a big topic. I only recently became aware of that because, I think it creeps up on you when you go from small pilot projects to big projects. But this is a huge thing when something desyncs, some calibrations don't work. I think the consumables part of scheduling is easy, but this whole conflict detection, I think we heard also about this in the previous presentation, that I think is an important thing. And as I said, it creeps up on you and you have no one who is familiar with it. And so that becomes then a stall in your project. Lastly, and I put this here on top because I really think, if things are working, that's great. But if no one uses it, that's not so great. And one of the biggest barriers for adoption is nicely, simple, structured, visual tools. So our experimentalists want that. And if they don't have that, they will most of the time not use, even if you give them the greatest tool and algorithm. So that's much about my wish list. Again, many thanks. And of course, I'm there in the chat for any questions. Thank you.
Thank you, Martin. So our next speaker is Jesper Sondergaard Marino from Novo Nordisk. So please, Jesper, you can turn on the camera and share your slides. So okay. You are muted. Okay.
Can you hear me now?
Yes, perfectly.
Okay. So I have put together a slideshow called Everything Everywhere All at Once. And probably you have heard about this Hollywood movie. This is a story about some of the challenges we had when implementing a small biophysics injectable formulation miniaturized assay system called BIFMAS, but it would be the same challenges also for larger systems. So before I start, let's have a corporate slide about Novo Nordisk. And one of the things I'm really proud of is that we are actually serving more than 45 million people living with serious chronic diseases. Yes, and that's all the time I'm going to spend on this slide. So some of the challenges we face at a large pharmaceutical company like Novo Nordisk is that we have a lot of different IT systems across the organization. Some of them are custom legacy systems and some of them are commercials. And so if a technician goes into the lab, some simple experiments require that they register things in multiple different IT systems. So we have a lot of different commercial schedulers for our lab automation systems, and they don't have a common way of programming them. We have also many different liquid handlers, and there's no common programming liquid handler programming language. So, and again, a large organization means 2 silos, slow handover of plates, information, and data. So orchestrating across an organization can be difficult. So back to the robot in this example. It's a system for doing biophysics in a miniaturized format in 384 and 1536 well plates. So it's binding assays, physical stability, solubility, and self-association. And one of the challenges of this system is that it actually has 3 different liquid handlers that have to work together to be orchestrated in order to create these plates. So the workflow you have to go through to orchestrate something on this is that you have to obtain a list of samples from your IMS, the inventory management system. You have to design the assay plates. You have to program your liquid handlers, all 3 of them. You have to calculate all the stock solutions, and then you have to program and start the scheduler. But that's just part of the story, because we have all these IT systems at Novo Nordisk. We have to register things in our Novo Nordisk compound database. We have to obtain the barcodes from the correct serialization database. We have to create our assay plates in another system, and we have to register the raw data. And then we also have to write our electronic notebook in a 5th system. So, and that is just to work by being in compliance. And what I've come up with a solution for this challenge here is to orchestrate this with a Streamlit app that basically conducts all the information flow and gathers all the information needed to start a workflow. And then it ensures that that the information is needed to program the schedulers and liquid handlers and to register everything everywhere all at once. And as it turns out, you can now start a workflow on this robot with only 5 mouse clicks. You select the assay, you select the source plates, and then you can basically tweak the assay itself. And then here I'll just say I want to run this assay in 2 different buffers. And then you just click 1 click and it programs the robot and registers everything everywhere all at once. So a little bit view behind the scene here. So there's actually some Python code on this slide here. You have 31 lines of code that describes how an assay is set up on the system here. So you have a source plate finder, which basically shows the source plate finder on this on the website. You have a buffer picking where you can select the buffers, and then you have the logic here that describes how the plate is to be produced by the Mantis and the Echo in this case here. So we have this platesmith package that abstracts the liquid handling and makes it into very small code. And then you have a randomization where you can randomize and then this standard visualization here just shows the plates, shows the liquid transfers, and also you can show the liquid handler file and generates these buttons that where you can just send everything off. And when you then go to the robot and you want to run everything, you get the inventory system here, which is basically the paper that is in the printer ready to be printed. And then you select the order that you want to run. And it already shows you where things are on the robot and what's missing to run the robot, which is the 2 source plates here. So you need to add them, and you can do that with a single click, and then save liquid handlers and start the job. So that was perhaps 8 clicks you need to do all the things here. So this is sort of a description of how the challenges we see, and maybe this is not scalable up to when you have a robot that or a series of robots that has to orchestrate things, but it was a sort of a solution we had for this particular robot here. And if any of you are interested, there's we have public, made two Python packages public. There's a Momentum PyClient, which is the Python package to interact with the Momentum. And then we have the process optimizer to do Bayesian optimization in closed loop.
So thank you, Jesper, for the great talk. We are starting with the presentations from the non-commercial orchestrators. So there will be a total of seven presentations. So we can start with Hyuk Jun Ju, hopefully I pronounced it correctly, from Berkely Lab. So he already shared the screen, so I think that we can start.
Okay, am I coming through right now?
I can hear you and I can just like see the slides. But you have, we can see the next slide. You have it in presented mode, in presenter mode, sorry.
Okay. Am I coming through right now? So please just check my voice.
Yeah, we can hear you.
Okay, got it. And okay. Good morning, everyone. It's a pleasure to be here. Then I'd like to say thanks to AC Consortium for organizing this nice workshop. My name is Hyuk Jun Yu, and I'm currently a postdoctor in Garber and Desiders Group and Lawrence Berkeley National Lab. But the work I'll be presenting today is from my previous work at KIST in South Korea. So that I eventually developed an operating system which called as Octopus. It is kind of the acronym, and it stands for Operation Control for Task Optimization and Job Parallelization via User Optimal Scheduler in Self-Driving Labs. So today I'm going to share about the Octopus today. I think you guys already have a deeper understanding about orchestration software in Self-Driving Lab rather than me, I guess. Then I think I can skip to introduce the definition and the roles of orchestration software. And in a nutshell, the conventional operating system was mostly built as single user environment to optimize single properties and single materials. But what if the different researchers want to develop different materials or different properties using single self-driving lab? This limited architecture of orchestration software that is only suitable for single user environment create very significant bottlenecks as soon as more users want to explore the diverse research goals. This leads us to the fundamental challenge, like how do we design orchestration software that can effectively manage chemical experiment in parallel? So in this question, we have two keywords. The first thing is, how do we design the tool? Like it is kind of the methodology, and the second keyword is more close to the how do we parallelize our experiment in self-driving lab. That's why I built KIST operating system inspired by Octopus. The key innovation of Octopus is centralized and modular architecture. And this architecture is broken down into the three main parts. The first thing is interface node, which looks like the mouse of Octopus. And interface node is kind of the user entry point. And a researcher can design a new experiment by selecting AI models or experimental modules, whatever they want, and just submit as a job. And the second thing is the master node, which looks like a head of Octopus. The master node is kind of the organize all of the operation in self-driving lab. The final thing is the legs of Octopus, which called as module node, is kind of the task-specific experimental devices for each chemical task, such as batch synthesis module or flow synthesis module or like UV visible spectroscopy module. Even though Octopus was designed with a multi-user self-driving lab in mind, it still doesn't overcome the challenges that enable to parallelize job execution so that the bottlenecks will be happen in this occasion. For example, if one job is active on the magnetic stir with the 16 resources, other job cannot parallelize. Other job cannot parallelize its same stirrer, even if there has idle resources according to in this figure, the question mark represent the idle resources. So even if there is a 12 idle resources, but we cannot parallelize the experiment. To answer this question, we have a question like, how do we unlock the full operation capacity of experimental devices and ensure that no resource is left idle? And to answer this question, then we conclude that implementing a scheduling algorithm is no longer optional. It becomes essential for truly multi-user environment. So that therefore, Octopus leveraged the user optimal scheduler with the two key strategies to solve this challenge. Like the first thing is the job parallelization, and it takes advantage of the device standby time, where it is not physically moving, but is simply waiting for the next chemical task, such as the React task in synthesis module. In React task, because there is only rotated the magnetic bar to mix the solution homogeneously, but it's still not moving like such as the robotic arm or solution dispenser or powder dosing system as well. In that case, we call the device standby time. And job parallelization recognizes this device standby time and intelligently initiate the other jobs in parallel, effectively leveraging the time that would be wasted. After that, our second strategy is closed packing scheduler, and this purpose of algorithm is to split the job for leveraging the idle resources as much as possible. For instance, if job ID 1 and job ID 2 is submitted, and if the job ID 1 and 2 is submitted, which requires for 8 resources and 4 resources independently, then there's only 4 resources left on the stirrer in the batch synthesis module. But if the job ID 3 is submitted, which requires for the 8 resources, then just the closed packing scheduler split the job and allocate into the idle resources that we can parallelize the experiment. Okay, and with this user optimal scheduler, then we just tested 11 jobs to Octopus for comparing the first come, first serve, which is the most popular scheduling algorithm in computational science or scheduler applications. And on the left side of the figure, then the first performance table is throughput the batch synthesis module, and the second performance table represent the throughput of UV visible model, which is kind of the characterization model, and the x-axis is the time, so that it looks like highly inefficient, which has many gaps in performance table in this UV visible modules performance table. Then compared to the user optimal scheduler, then our scheduler intelligently maps the landscape of the entire workflow, monitor available resources, and fills those idle gaps compared to this performance table, as you can see this figure, and just we can save the time according to this region with the red dot line, and this region represent the saving time, time saving. And therefore, with the user optimal scheduler, then we just save our time and decrease the job total time from almost the 17 hours to the 9 hours, so that we can prove the performance of the user optimal scheduler. And in practical approach, one of the biggest bottlenecks is the need for hands-on code generation and customization of Python script, as far as you know. And integrating a new hardware or designing a new experiment requires very complicated and time-consuming jobs and create a very significant barrier to entry for researchers who are not coding experts. To dismantle this barrier, then we created the Copilot Octopus with large language model powered system that partners with the scientists to automatically generate the necessary code in self-driving lab. So then we can prove and we can provide the scalability of Octopus to the diverse applications, such as a drug discovery or the material science or chemistry, something like that. And here's my KIST autonomous lab team members, and we got funding Korean government, and thanks for funding to me. Yeah, and this is the KIST autonomous lab demonstration video. Then we'd like to share the video to audience. And thank you for your attention. Then if you have any question, please chat to me. Thank you.
Thank you so much, Hyuk. So our next speaker is Bastian Ruehle from Bundestal for Materials Forschung und Prüfung. Sorry about my German, it's not the best. But please share your camera and you can start.
Yeah, thanks for the introduction. So yeah, it's Federal Institute for Materials Research and Testing. Can you see my screen? Okay, then let me get started.
We can see you and listen to you perfectly.
Perfect, thank you very much. Yeah, so let me tell you a little bit about our orchestrator, which we call Minerva OS. It orchestrates our self-driving lab for nano and advanced material synthesis. Why does the slide not change? Here we go. So this is what it looks like. It's made for synthesizing nanomaterials, mostly in a wet chemical synthesis lab. We have these different hardware components here that are orchestrated by it. I just brought a very brief video to show it in action. I'm not going to play the full video, but so the idea is essentially we have this robot arm that can serve all these different stations that can perform synthesis tasks that are commonly done in a wet chemical synthesis lab. So you can add small amounts of chemicals with an Eppendorf pipette, and you can add larger amounts with these kind of syringe pumps. Then we have, for heating and mixing, we have regular hot plates. So the robot arm can just put a flask on a hot plate, it'll clamp it down. You can lower a condenser on top of it. And then you can set the temperature and the stirring speed and these things, all these process parameters. For separation, we have a centrifuge here that can centrifuge the nanoparticles. We can redisperse them afterwards with a probe sonicator. So this gives us the opportunity to synthesize these nanomaterials, and then we can also do some inline characterization, which shown here is a dynamic light scattering instrument. So this can characterize hydrodynamic diameters, which tells us something about the size and the surface charge. Now, for orchestrating this thing, we have our own equipment, which is called our own orchestrator, which is called Minerva OS. So it's the centralized hardware control system that controls all the hardware. And on my to-do list for this year, one of my New Year's resolution was to actually finally put in a Silo 2 and OPC UA layer in between. So this is easier for integrating new devices. And we have our own self-written high-level Python API, which has a lot of built-in heuristics. We have a simple task scheduler that is based on a priority queue for multi-threaded parallel reactions. And we have a node editor that looks like this for building the workflow. So some people call that actually a flow, what I call a workflow here. Yeah, we have a ELN and LIMS integration. So ours is called OpenBIS, but yeah, so all the data, metadata of the characterization and also of this workflow gets uploaded into this ELN system. And we also have some basic machine learning and AI for closed feedback loops and active learning tasks. So this is what it in principle looks like. We have all these different components in our lab that are connected with different things. So we have just USB, like Arduinos that are connected with USB. We have other hardware, for example, the one that controls the DLS is connected via just local area network. Some of the hardware is on Wi-Fi, some of them are just on COM ports. And depending on that, we just have to talk to them in different ways. So for these ones, we just have our own custom protocol. For some of them, we have vendor-specific APIs, so software development kits. Some of them, you just send direct commands over the serial. This can just be like an ASCII string or a hex key, or a Modbus, you have to write to the registers and so on. But yeah, so this is taken care of, and then this is where we want to put in the Silo 2 OPC UA layer. And then all of these are kind of gathered in different Python classes that are then, again, they inherit from abstract base classes. So pretty much all of these are addition hardware. So they all implement this abstract base class addition hardware. These are all controllers, and then we have heating hardware. And so we have a couple of abstract base classes that are defined, and then these sit under them. On top of that, we have our task scheduler. I'll talk a little bit more about this later. And then on top of that, we have our high-level API where you can just say add chemical, and then essentially the backend or the orchestrator will take care of by figuring out where the chemical is, which hardware is suitable for adding it, and then bringing the flask there, adding the stuff, and then putting it somewhere else. So these are the very simple commands that you can then send. Here's an example of such a command and such a of the heuristics. So you define your three chemicals. In this case, it's ethanol, ammonia, and TiOS. And then so you say the amounts that you want. This is very flexible. You can just specify a molar amount and a concentration, or just a amount in milliliters. And then you tell it, okay, take the reaction flask at these chemicals, then heat it up to 80 degrees, 30 to 300 RPM for 2 hours, and then put the flask in storage. Then it's done essentially. And this is enough. This is all you need. So all the other questions that pop up, like how many milliliters of ammonia solution do I need? It just says you want 0.01 mole of this 30% solution, but how much is that in milliliters? It'll figure that out for you. So it looks up the density and the molar mass, and it calculates that, or how many milliliters is this real chemical here? So what is 2 millimoles? Again, looks up the density, does the calculation, which addition hardware it can use, which pipette it should use for small amounts, for large amounts. Is the flask big enough? Are you trying to put 500 milliliters in a 10 milliliter flask? So all these different questions that pop up during the execution that are not specified here are taken care of by the internal heuristics. And also it takes care of the priming, of the purging, and all these things for you. For the task scheduler, first when I looked at this, I started off with the job shop scheduling, and that's kind of what everybody does, I guess. But then I quickly ran into this first problem, which was that we have a very flexible system with 14 different stations. So then when I wanted to put in the task of transfer something from hardware A to hardware B, I needed to know how long will it take the robot arm to go there. And this then, of course, kind of has a combinatorial explosion, and you have to retime all these different things. Now I can say that doesn't matter too much. Just take a worst case scenario of 2 minutes and it's fine, which I also thought of doing. But the bigger problem for me was that sometimes I didn't even know the timings. So they can depend on dynamically chosen parameters. For example, how long does it take to cool the reaction down before I then can centrifuge it? And this depends on how much solution I have in the flask, which might be a parameter I want to vary. It depends on the heat capacity of the solution in there. So I had no easy way of gauging or of guessing this parameter. And then if I always just take, I don't know, 1 hour for cooling down, at some point this becomes very inefficient. This is why the task scheduler that we were working with is essentially it's based on a priority queue. It still parallelizes tasks, but it respects the order of operation. So you can group certain tasks together so that it'll always, for example, add the solution before it heats it. There's no point in saying, well, the addition hardware is busy, but the hot plate is free, so let's just heat it without adding anything, and then we add the stuff later. So this is, of course, needs to be respected. And then we need to avoid these race conditions and deadlocks, all the fun that you have with parallelized and with multi-threaded programming. And we can also avoid bottlenecks by prioritizing certain tasks. So we can, for example, say, okay, the centrifuge is a bottleneck. So if there's a centrifugation task, always like serve the centrifuge first and then take care of the other stuff. For generating the workflows, we have this node editor here. It's a graphical way of putting together these workflows, or some people call them flows. I call them workflows, but yeah. So and then you can then sort of the user can just kind of draw this, and then this gets translated into Python code, and you can execute it. Another big advantage is that you can actually easily extract a knowledge graph from that. So let me just show you real quick what it looks like. So this is this node editor. You can just add these nodes and then you put in the information there. So you have these chemicals here and you put a second chemical in here. So that's the sodium hydroxide. And now we want our reaction flask, which is just a round bottom flask here. And now we want to add the chemical to it. And then you pretty much just connect the yellow to the yellow and the red to the red. And based on this, you can then just build up the entire reaction. So now we have a heating step. So we want to heat to 75 degrees and stir at 300 RPM for 2 hours. So you just put this information in there, connect everything up, and then you can build pretty extensive workflows. And you can also have a machine learning, a LLM actually that kind of builds them for you. So we've published an LLM as well that you can host locally on your computer. So you don't need to upload anything to OpenAI or anywhere. You can just run it locally. The last thing I really want to talk about very briefly is these knowledge graphs. So we can go ahead and from these node networks, we can then extract that and turn that into a knowledge graph. And we are currently working on an underlying ontology. This will probably be published this week or next week, as a preprint at least, where all of these have semantically annotated properties. And then this also helps then, of course, with interoperability of the workflows. And it should also help with making it machine readable and AI ready, because an AI can read the semantic annotations and then it can know what this is. And lastly, I'm not going to talk about this, but we have these different machine learning algorithms that can help you with doing online learning and then optimizing it. Here it's just shown for example surfaces. There we're also working on a real example right now. But yeah, so that's our orchestrator. Thanks for your attention. If you have questions, please put them in the chat and I'll try and answer them.
Thank you, Bastian, for the great talk. So our next speaker is Ron Alterovitz from the University of North Carolina at Chapel Hill. So please, you can share your screen and yeah, the floor is yours.
Okay, great. Do you hear me and see me? Okay, great. Yeah. So thanks for organizing this workshop. So I am Ron Alterovitz from the University of North Carolina at Chapel Hill in the Department of Computer Science. And just as robots have had a big impact in speeding up manufacturing in factories, we are now working toward developing robots and automation tools that integrate into chemistry and material science labs to turn these labs into automated factories of discovery. So a common paradigm for advancing research in chemistry and material science is the design, make, test, analyze cycle, or DMTA. So we can now use AI to analyze data and propose new designs of chemical systems or materials. And robotics and automation can help automate the physical steps in the lab for making and testing to produce a lot of data for AI. So with computational and physical automation, we can now make the lab self-driving. So how do we classify how autonomous a lab is? So in a paper that we published in Science Robotics, we defined 5 levels of automation for self-driving labs, which were inspired by the automation levels for self-driving cars. At level 1 assistive automation, the physical automation automates a single step of a synthesis or characterization. Moving up to level 3 conditional automation, an entire process is automated but requires humans to set up the system and handle unusual conditions. And at level 5 full automation, the entire process is physically automated and all humans can do is stop it. So essentially, as we increase the levels, the role of the human declines and the burden on the automation system rises. So for increasing automation, we've developed robots and software to automate tasks in labs in chemistry and applied physical sciences. So we've developed mobile robots that transport samples and can perform manipulations at different stations. We've also developed robots that handle substrates and solid materials. And when we look now at like a fully autonomous lab, it will contain robots like the ones that we've developed, as well as many other robots and instruments that must be scheduled and operated to complete experiments. And coordinating all these different items is hard. So this has led us and many others, right, to develop orchestration software to orchestrate these autonomous labs. So our experimental orchestration system, or EOS for short, is open source software that offers a comprehensive foundation for implementing and running lab automation. So EOS includes a framework in which you can implement tasks and devices using Python, define lab layouts and experiments using YAML, as well as define optimization objectives. EOS also includes a runtime that takes the information that it got from the framework and runs the lab. It schedules and executes tasks on devices, collects and organizes data, and optimizes experiment parameters based on AI or a built-in optimizer. So EOS is middleware that speeds up creating the software that runs the self-driving lab. So EOS is named after the Greek goddess of dawn, Eos, which we feel echoes the early stages of autonomous experimentation that we're in and its great potential. So there's an increasing number of orchestration software packages available, as we saw in the opening, and some of the really nice systems that were just introduced this morning. So why use EOS? So in our case, we aim for a comprehensive solution, and I'll describe some of its top features next. So first, EOS makes it easy to build closed-loop experiments and campaigns. You can optimize parameters for an EOS experiment, and you can run a campaign to maximize an objective, and EOS will manage the execution. In particular, EOS supports the full DMTA cycle. So for the design step, it provides facilities to specify experiments with static and runtime validation for errors, as well as specifying dynamic parameters to be optimized. For the make and test steps, it optimizes execution with scheduling and aggregates results. And for the analyze step, it enables launching data analysis tasks, including AI, and provides data storage for small and large files. So the second big feature is EOS is AI native. Data, AI, and physical automation can be tightly coupled. So EOS makes it easy to integrate AI into the DMTA cycle by getting outputs from the test step and specifying inputs for the make step. You can use the built-in Bayesian optimizer or use your own customizer, including AI-informed optimization. And using the built-in Ray framework integration, it is easy to do distributed data processing, reinforcement learning, and data transfer of large data such as tensors. So the third feature is EOS provides standard interfaces for writing device drivers, tasks, experiments, and optimizers. The Python and YAML interfaces are designed by computer scientists to be clean and modern and allow for greater reproducibility and reuse. So in EOS, you specify the core components needed for lab automation: devices, tasks, and assets. Devices are laboratory apparatuses or compute hardware, like a robot arm, a GC, an Arduino board. Tasks correspond to distinct actions that may utilize some devices and operate on samples, for example, moving a sample on a magnetic mixer. Assets are physical objects in the lab that can only be used by one task at a time. So devices are special types of assets, and other assets include like sample containers, slots on an apparatus where a sample can go, and so forth. Fourth, EOS is a scalable and distributed. So it uses a hierarchical execution model, which allows you to separate concerns so you can scale better and allow for increased flexibility across cases. Users write code as Python plugins, which are loaded by EOS at runtime and automatically deployed on the relevant computers. EOS packages organize device drivers, tasks, labs, and experiments, and allow distribution with others. And also, EOS is built upon Ray, which is a distributed framework used by top AI labs and companies and proven to scale, whether you want to use it on one computer or thousands. So the fifth major feature is that EOS offers broad support for a variety of devices. So this support is made possible by three different mechanisms for integrating devices. You can implement EOS device drivers directly within EOS. You can directly use vendor-provided drivers, such as via REST API. And we also have support for Silas servers as well. So the sixth major feature is that EOS simplifies data management. EOS moves inputs and outputs automatically, such as storing the files generated by a task. So everything is recorded at every step of the way. So you write your code in EOS and it will handle that data flow for you. The seventh major feature is support for optimized scheduling and asset allocation. The EOS has a global scheduler that optimizes the execution of experiments by minimizing their duration or some other objective and efficiently allocating devices and assets like sample containers. The EOS schedule can handle multiple experiments at the same time within your lab. And our built-in implemented schedulers use methods from the operations research community, like a greedy policy and CPSAT, to compute optimal schedules based on constraints. So in summary, our goal with creating EOS was to be comprehensive, so offering features that are needed for a variety of R&D workflows. So in closing, one of the goals in the workshop was to think about what we should standardize as a community. So creating a comprehensive orchestrator requires two major pieces. The approach we took at EOS was a framework and a runtime. The framework is how the user code is written, what abstractions are used and how they relate, from low-level device drivers to closed-loop experiment campaigns. And then there's the runtime, which is how the user code is executed. So how conflicts are avoided, how communication with components happens, and so forth. So when thinking about standardization, do we need to standardize both? We think that the framework will be a good place to start. So standardizing the framework will create a common language that will facilitate code sharing and reuse and ease of integration of a wide variety of devices into new autonomous labs. So if you would like to learn more about EOS and how it can help in lab automation in your lab, you can scan this QR code or visit the GitHub repository or check out the paper. Also, my research group has experience helping teams in chemistry and material science set up automation to gain the benefits of faster and more reproducible workflows. So if you're in the process of setting up such a lab, feel free to reach out to my research group, and we'd be happy to see if we can help if some of our tools can help you. So with our projects, we're hoping to enable improvement in the level of automation in autonomous labs. So thank you again.
Thank you so much, Ron. So yeah, our next speaker is Christian Frank from the University of Glasgow. So please, as always, turn on the camera and just like share the slides. The floor is yours.
Thanks for the introduction. My name is Christian Frank. I'm a research fellow in the Cronin Group at the University of Glasgow, and I'm team leader in the computation team that deals with developing KDL and also the computer platform. So when I think of chemical procedures, they're usually written in prose, which means natural language text. And if you want to use this for automation and orchestration as well, there are some fundamental flaws. Number one, it's often ambiguous and subjective, so we need human interpretation for it. It's incomplete, which means we need tacit knowledge. For example, how big is the column, how much extraction solvent is used, and the format itself is outdated and it's virtually unchanged since the first publications in chemistry over 150 years ago. This results in a high failure rate in reproduction. Our solution to this is the chemical description language, which provides a precise semantic standard. It's a file format that is both human and machineable, and it's hardware independent. It describes a chemical process, for example, add 5 milliliters of something rather than hardware instructions. Given the correct drivers, it's universal and can be used on any robot, and this will give a higher reproducibility. A KDL file is an XML file, and it has multiple sections. One of them is the synthesis section that contains hardware. This declares virtual vessels, such as reactors, flasks, and this is all the vessels where chemicals will be stored and reside in. These vessels can be referenced by their ID in the procedure section, which we will see later. There's a reagent section that, of course, defines all the chemical inputs for our procedure. It can include some properties such as molecular weight and the role to show chemical intent of this reagent. And the most important part is the procedure, which declares the synthetic action. It can be further subdivided into specific blocks if you wish, and it contains chemical intent and operations such as add something, stir the mixture, heat chill, irradiate, and so on. Want to generate the KDL file, you could either do this by hand using just normal text editors, since it's a human readable, but you can also use tools like SynthReader or Clarify from University of Toronto that uses or parses prose, extract the synthetic actions, converts this to KDL, and which can then be executed on the platforms. We have a tool called ChemIDE, which allows you to parse text. So you go to this website, then you paste the text inside, you can translate it to KDL, then change the step properties if you wish to, inspect the KDL code, check the reagents and the hardware to see if everything is correct. We said KDL is hardware independent, So of course, if you want to execute the KDL on your specific platform, you need more information. For this, for example, if you want to use this computer here down on the image, you need a graph. It's the graph representation of how the devices are connected. And this provides the hardware knowledge. This is then fed into the compiler, which validates and maps the chemical steps to the hardware and separates them into sub-steps. Why do we need these sub-steps and further base steps? Imagine you want to move something from node A to node B. At least if you use valves and pumps, you cannot do this in one step. So instead, you need a first step that moves into the pump and then a second step that moves it into the vessel. Eventually, these base steps are then executed and communicated to the hardware. Some nice features that we've added in the recent years are reaction blueprints. You can think of this like a macro. So you define a template, example, a Grignard reaction, where I say I have a reagent that is a Ruehle halide magnesium reagent, a proline, and the solvent. And this is the procedure that should be done with these reagents. And then if you later want to use this in your procedure section, you specify Grignard, and then you give the concrete reagents that you want to use, as well as a scale. Another thing is parallelization. So imagine you're having a reaction and you want to, of course, use all the instruments and orchestrate this a bit better. In this case, it's a recycling reaction of a catalyst. So after the reaction, you run the recycling step, you put the catalyst back into the reactor, and while the second reaction is running, you can work up and isolate your product and repeat this step. And this resource allocation does save a lot of time in the overall procedure. As I said, KDL is hardware independent, and there has been several platforms demonstrated to work with KDL. Among them are Novo and Franca robotic arms, OpenTrons, the computer, and we also have been working on a portable version of the computer. A quick introduction of what a computer is. So computer evolves around chemical hardware, standard laboratory glassware and instruments that is equipped with sensors, and these can be analytical devices or also your stirrer, which usually has a temperature sensor. Then it adds some custom-made sensors and also cameras that you can use to colorimetrically check your reactions. Of course, you need some data processing, plateau detection to figure out when your reaction is done, and you need to control this somehow. And for this, we, as I already mentioned, use KDL. The last bit we are currently working on is process recording, where we're recording operational technology data from all our sensors and devices, store them in a database, and this can then later be used to fingerprint reactions, but also check whether the reaction process is correctly. In our communication layer, we use a package called PyLabber. That's an in-house package. It's a unified capability-based API that distinguishes between measure and control and measure capabilities. So for example, a rotovap can control and measure temperature. It can lift its arm, apply vacuum and stir. And a ICA red whisk hot plate, for example, can not only measure temperature and control temperature and stir, but it can also weigh at pH and viscosity. So instead of just defining it as a hot plate, we define it as a device with these capabilities. So far, we have devices from many manufacturers, and for in-house built devices for prototyping, quite important, we have an additional package. It's called Circuit PyLabber that allows you to work with any prototype you built in-house. And here you see a computer running. Our ideal goal is that the computer does the whole synthesis for you. You just set up the reagents, and then you walk away and come back to your final products. You can see it operates with separations. It then evaporates your product and dries it, builds it back, washes out the flask, precipitates, and then you end up with your final compounds. This I'm already at the end of my talk. Thank you very much for your kind attention. And if you're interested in getting a computer, please get in touch with Professor Lee Cronin.
Thank you very much, Christian. So our next speaker is Noah Paulson from the Argonne National Laboratory. So Noah, you can start with the presentation soon. You are there. Okay.
Okay. Can you hear me okay?
The floor is yours. Yeah, everything is working.
Apologies, I have a bit of a cold, so I might sound a bit different. I'm representing the Rapid Prototyping Laboratory and some other folks, so I'm not going to be able to acknowledge them fully, but they're at the bottom right of the screen. And okay, here we go. So I'm a computational scientist at Argonne. I run Argonne's Rapid Prototyping Laboratory. I see us as a repository of expertise in autonomy development and enabler of autonomous science across Argonne, so that's largely the role we've been playing. We have 3 key objectives. We want to develop comprehensive software infrastructure for laboratory autonomy. A lot of others have described this, but I think that our goal specifically would be to develop all of the infrastructure necessary for a cloud laboratory. So that means that there might be multiple instruments across multiple laboratories and then also multiple users. We'd like to be able to expand the diversity and the complexity of the workflows that we can address. So this means things like error handling. It means agnostics to domain science. It means thinking about scheduling and all those other aspects of orchestration. And then finally, it's to enable domain scientists by having this centralized expertise in the modular software. Here's an example of one of the labs that we've been integrating, and I'll show another one afterwards, but this is our chemistry laboratory called Rapid 200. Like everyone else, we have our ability to create samples. We have the ability to move samples around, and then the characterization aspects. So for example, we have our OpenTrons OT2 and our PAL3 robots for liquid handling, as well as a Big Kahuna robot that's not pictured. We have our UR5 robot on a rail, so it can move around and pick up samples and put them in other places. And then finally, we have the characterization via ICP and NMR. So this has all been integrated with our orchestration tool, which I'll be talking about in a slide or two. Yeah, this slide, actually. So the software that we develop is called the Modular Autonomous Discovery for Science Package, or MADSci. We deployed it across Argonne in biology, chemistry, material science, and more. It's currently in beta, but we are very actively developing it and would love to have people try it out, so let us know. So the objective of MADSci is to coordinate these autonomous workflows across different devices, pretty standard in terms of orchestration. So again, it's open source and Python based. One of the key design principles behind MADSci was that it would be modular. So sometimes for a given application, we might not want to use all of the components of a given orchestrator tool. Maybe somebody has a resource management and laboratory information management system that they want to use. You're not forced to then use what MADSci's solution is. You can use that component and then use the rest of what you'd like from MADSci. They're also designed to be hackable. So if there's something you want to modify, that's not a problem at all. Again, vendor agnostic. I think this is pretty common. We want to be able to integrate devices from any vendor and then work from a single device to multiple devices in a single laboratory to multiple laboratories working in concert. We talked about it being domain agnostic. It's also designed to be powerful so that you can have granular control over anything that you'd like to do with your instruments in your laboratory. But we still want to have the simplicity of being able to define an experiment in a parsimonious manner. So I think there's going to be some effort up front in terms of setting up your laboratory. I think that's going to be the case for any orchestrator. But in terms of executing and running, we want to have a simple way of doing that. Not quite yet to a full GUI control of this, but that's obviously a desirable thing to get towards. So how does MADSci work? We have our devices layer on the right. The most simple case is just these 3 devices: a liquid handler, robot arm, and a plate reader. We then, given the different APIs that might be present for these instruments, we have to define node standards that allow us to interface between our MADSci system and these devices in a seamless manner. And then on the other side of things, we have our experiment application. This is where we would define this Python file, 100 lines of code or equivalent, and be able to include data management tools, artificial intelligence tools, high-performance computing, so on and so forth. And the interface between this experiment application or this experiment definition and our nodes are the manager layer. So this could be in terms of coordinating between these different instruments, keeping track of resources, keeping track of data, recording events that might be happening in errors, anything that any task that is required of our autonomous laboratory beyond just running commands on the nodes and defining the experiment is handled by this manager layer. And that's about all the detail I'm going to go into for this particular venue, although I think that in a future workshop we'll have a lot more chances to talk about details. But please take a look if you're interested. Here's the QR code on the right. In terms of our next steps for the Rapid Prototyping Laboratory and MadSci, everybody's been talking about scheduling. We're have a relatively rudimentary scheduler at this point, although we are looking to expand that so we can accommodate these simultaneous experiment scheduling challenges. Vision-based location tracking, I think this is critical. One of the challenges that we faced in these sorts of workflows where we actually have to move samples around, it's not like a fully closed loop liquid system. This requires that we are calibrating positions in a very let's say, time-consuming and painful process. So that alone is a motivator for having the ability to track the locations of samples versus your instruments, and then on top of that, having the flexibility to put samples where you want to. This is sort of a robotics challenge. And then finally, human in the loop and autonomous error handling. So again, this is a place where APIs that can be accessed by AI agents would be quite helpful, but also there's a need to understand what are the challenges of the actual experiment, what sort of errors can come up, and being able to anticipate that before setting up this sort of system. So another set of examples, one of the most let's say mature areas of our application is in autonomous biology. We have two different laboratories. Rapid 446 is our general biological laboratory. And then we have our Rapid 350 laboratory, which is our biosafety level laboratory. So it's just enclosed in this fume hood. And across these two different laboratories, we share 4 experiments. Most of them run on this 446. These first 3, so we're looking at environmental impacts on biological systems, enzyme and pathway engineering, metabolic pathway engineering via synthetic biology, and so on. The more detailed example is actually performed in this Rapid 350 laboratory, which is the discovery of antimicrobial peptides. So these are essentially short protein sequences that show activity in retarding the growth of different types of bacteria that might be harmful. So you can see this fairly complex loop on the left, which involves databases of antimicrobial peptides, AI approaches to cluster and understand the similarity between these different amps. And then we use a protein language model to suggest mutations of existing sequences, filter these peptides so that we can then order them and then deploy them at our self-driving laboratory and evaluate the success of these. So you can see on the right an example of this with E. coli, and the darker the color of the well, it means that there is not as much bacterial growth. So on the top row, we have our native antimicrobial peptide that would be found in nature, and you can see that there is some activity, but only at the highest concentration of the antimicrobial peptide. But in our modified antimicrobial peptide, we can see that we're showing increased activity even at lower concentrations of the amp. Okay, and then moving on to the last slide, I just want to sort of talk a little bit more about the bigger picture of orchestration and laboratory autonomy. So I've been working with this group called the Challenges and Opportunities for Facing Laboratory Autonomy, or COLA. We are a team of, not a team, I would say a community of developers and users of laboratory autonomy, including companies, national laboratories, the AC, AFRL, and universities. The group is just a discussion group for talking about these sorts of challenges and opportunities. I'm leading the discussion and also leading a community perspective paper, which we should have a first rough draft coming out soon for the community to take a look. So please reach out if you're interested. But the goal here is not that this to be something where I'm just directing different activities, but that everybody is sharing the activities that they're pursuing and allowing this community to move forward together towards this democratization that we're interested in. So some examples are organizing these workshops and hackathons like the one we're in today. We shared that with that group and talked about the planning process, as well as developing educational resources. This is an activity that some of our group members are moving on. So it looks like I'm running low on time. So I just want to throw up a thank you slide, and I'll talk to you a little bit later at the closing remarks.
So thank you, Noah, for the great talk. So our next speaker is Robert Walder from the Air Force Research Laboratory. So Robert, you can just like put the presentation slides and then start.
Okay, for some reason it's not letting me turn on my camera, but hopefully everything else is working.
Yeah, the microphone is working and I can see your presentation.
Wonderful. All right, so everyone, I'm Robert Welder. I'm at the Air Force Research Lab in the US. We're based out of Dayton, Ohio, in Benji Maruyama's research group. And so we develop Aries OS, and we're now on Aries OS 2.0. So our kind of history is, so a little bit of history and term definition. We use Aries the way most people use self-driving lab SDL, but Aries is, to us, is autonomous research system. And then on top of that is our Aries OS, which is our orchestration software for facilitating this autonomous research. We've been in the field for a while. Our original laser CNT system is the first fully autonomous system for materials research. It was first fully closed loop in March of 2014, and you know, our well-known paper came out in 2016. We follow the very standard kind of active learning approach, which is small data. We do experiments one or a few at a time, right? Follow this kind of update, turn the crank, do a new experiment, and rinse and repeat until we're satisfied. For our laser CNT system, just for context, we typically do tens to hundreds of experiments per campaign, which translates to 1 to 2 weeks of real time in and around the human operator babysitter, their schedule. So one of the things that we're really, really proud of with the Aries OS 2.0 release that was, I think it just came out I think we formally released it in December, is this installation. One of the feedbacks that we've gotten before on our system is that it's, our system and others, is that it's very difficult to install. So very conveniently, I was given a new computer at work. This was like the second thing I did on it after I signed into my email, was to install Aries OS, and it is very nicely this simple these days. We support Windows, Mac, and Linux now. This has been tested on a few different several Windows machines, ARM-based Macs, so all the M1 stuff, or Apple Silicon stuff, and it's also been tested and shown to work on Ubuntu and Red Hat Linux systems. But so you can see all you have to do these days is go to our GitHub, download the launcher, extract it, fire up the launcher once you find where it is in the folder. It'll pop up this little window. Once you tell it that, you know, we're not going to try to destroy your computer, give it the appropriate permissions. It'll think about it, and then all you have to do here is click install. And so what this is going to do is go to the GitHub, find the release binary, download that, and start you know, plumbing certificates and databases and things together. You can see the configuration tab on this window lets you do things like connect it to, like, specify where it's going to be installed, connect it to a custom, you know, your GitHub for developing your system, and other things that we hope to add there in the future. So we'll just accept the certificates, and it'll crank through it. And what it's going to actually do is open our graphical front end in the browser. One of the things that we've done with Aries OS 2 that's different from previous installations is we've actually separated the front end and the back end. The back end runs as a constant process in the background, facilitating communication with hardware and keeping all of that stuff alive. And the front end is just simply a web page. In this case, the browser loaded faster than the back end. But once you're in Aries, you know, installation is that simple to get started. So just a little bit of history. Aries OS 1.0 still runs a few of our systems. Laser CNT is our first original system, and we have a few others running that as well. Aries OS 1 had a script-based experimental planner in a custom language, but it did have a lot of niceties like auto-completion and syntax highlighting. But we did things with an experiment script, an inter-experiment script, and a campaign closeout script. So what it's doing during an experiment, what it's doing between experiments, and what it should do when you're all done. So here's an example of a working dashboard in Aries OS 2. I'm not going to play this video but just for time's sake, we have two systems currently running that, our floating catalyst system and educational Aries. Like I said earlier, this is available on GitHub now, and we have a Journal of Open Source Software publication on this in review. Let's see here. So this is just a quick video poking around the software. There's no hardware integrated in this, but showing off our campaign designer. One of the things that it lets you do is set up kind of environmental variables that are campaign specific. In this case, it's just a nonsense scalar that I'm putting into to show this feature off. But this could be something like a total flow rate that you can't exceed, or a chemical that is specific to the campaign, loaded in a syringe pump, for example, that doesn't support telling you what's in there. It just has a flow rate, for example. But then you click through these startup scripts, experiment templates, and campaign closeout scripts. You would do this kind of stepwise definition of what you want your experiment to look like, device by device, step by step. Again, all you're seeing in here is, the kind of default things that are built into Aries. And then we also have analyzer and planner inputs. And what you're doing here is, how we're going to analyze data and turn our raw data into an actionable output, and then how you're going to plan things. And then to actually execute it, you come over into the execution tab, you select the campaign you want to do, you say the number of experiments you want to do, how often you want to use your planner, and then you would click play. The other thing that I want to point out in this is our little experiment notes over in the side here, and this just gives you a place to add notes as you're going. Something else that we're kind of proud of in this new release is our software e-stop button. One of the things when you integrate a device into Aries, it must have a safe mode defined, and so when you click this e-stop, it sends a command to go to safe mode to every device in the system. So Aries 2.0 is built on a core shell architecture where we separated the core from the shell, which are the various modules that you can plug in. So the core orchestration software is service-oriented, written in C# on .NET. It features this dynamically constructed Blazor UI. So when you integrate a device or a planner or something into Aries, it's able to feature advertise to Aries, and it will build a little dashboard element for you that'll show off everything in there. Communication between modules and the core is done by Protobuf and gRPC, and this supports local and remote modules. So you could have a planner, running on a supercomputer, for example, or locally. Our modules are designed to be software engineer out of the loop, so you do not need to change the course, anything with the core software to integrate these modules. The modules include devices, which could be a hardware or a software device, analyzers and planners. Fundamentally, they're language agnostic as long as you can encode it into the appropriate protobuf message. But we have released a helper PyAries library. Over here is the boilerplate that's available on GitHub, and this is basically everything you would need to spin up a planner with PyAries. You'd simply put your planning logic in this plan function, and then down here you would just add kind of boilerplate advertisement to Aries of what it needs to make that plan happen. As far as data management, I added this slide earlier as people were talking about it. Data is typically saved in two places. We have a central database that has, everything, the complete history of the experiment, the complete history of the experiments, the complete history of device states as you're just sitting there idly. And this is, written to all the time and is read-only, accessed only through Aries OS. And then we also have the experimenters database, which is kind of a traditional folder tree, a friendly place for experiment to experiment data to be placed. And you actually get to, when you're setting this up, you decide what goes in there, what is pertinent to the experimenter, so that you don't have to risk them touching your ground truth database. Just to go through really quick, we've got a few systems. Our original laser CNT system, our floating catalyst system, additive manufacturing. We've got our original AM Aries was a 1 and 2D printer that printed latex caulk. We developed a self-calibrating 3D printer using a webcam and integrated that into educational Aries, which is now been given to SUNY Buffalo and Chris Ray as an educational tool to develop, learn about autonomous workflows and develop analysis and planning softwares. We've got 2 flow chemistry systems here that I won't go into for time. But importantly, this is, here's a list of everybody that's been involved in the Ares project at various states. This wouldn't be possible without a huge team of people. And then just a really, really quick plug for a workshop that we're looking to put on in March or April. The idea is that we should only need to write a device driver once. We should be able to have or as close to total interoperability between orchestrators and this device architecture. So more information to come, but hopefully this is something we think is useful and timely. So thanks.
Thank you, Robert. So our next speaker is Hatem Fakhruddin from Johnson & Johnson, formerly at the University of Liverpool. So yeah, the floor is yours.
Okay, let me just share my screen. Okay, hi everyone. My name is Hatem Fakhruddin. Currently, I'm a senior automation scientist at Johnson & Johnson, based in Toledo, Spain. Before that, I was in the Andy Cooper group in the University of Liverpool. Today, I'll talk about Okra, which is our framework for lab automation and orchestration. So I'll start with the motivation for building this framework. So in 2020, we built our first kind of software architecture for lab orchestration and running autonomous workflows with mobile robots. Without going into details, the idea of that architecture was you feed a chemical recipe in a human readable form, that's YAML file that describes the sequence, and then the system will take that file, run the information for you, or run the experiments for you, or return to you the data. All the instruments were connecting using ROS, which is stand for the Robot Operating System, which is like a middleware used in the robotic world to connect robots and instruments and sensors and stuff. And we used that architecture to run three workflows. One that involved multiple robots, different instruments, also different custom instruments. However, after running these workflows, we were planning to build more workflows. So the goal, we noticed some problems we have then. So one of the problems we had, it was basically separation of concern. When that architecture was built, there wasn't a clear separation between the parts that the scientists or the chemists will be focusing on and the parts where the automation or engineer will be working on. They were kind of all merged together. We use an outdated software stack. Well, we use ROS1 as our middleware to connect all the different devices together in robots. However, ROS1 was coming to the end of its life cycle, and the community, in robots, were using ROS2. An interesting kind of observation we found from our science users, they weren't happy about using the configuration language, where they were more interested in using a programming language, as they found it a bit limiting. The system was built in a very, at that time, also the system was built in a very coupled way to MongoDB database implementation, which kind of limited the system usability. And finally, also the system was, beside our effort to make it modular, accessible, still there was some the software was still a bit too cumbersome to maintain and to extend to new functionalities. So we decided to build our second iteration, which is the Okra framework. Okra is basically the idea behind it was to try to build a comprehensive tool set for accelerating material discovery. We wanted to empower both the physical, the scientists on the end, so they can design their experiments at ease, and also we wanted to empower the developers or the engineers on the other end, who kind of helped to bring this vision to life by integrating instruments and robots and whatnot. Also, we wanted to streamline the experience for both sides of the system, so scientists can easily learn how to use the system and get on with it, and at the same time, engineers or developers can also easily add extra features and integrate things in the system. And finally, we wanted to integrate new technologies, and such as adding AI generation for code. And also kind of new advances in kind of communication between devices. So the main features of this framework, it's fully Pythonic. What that means, it means like everything is written in Python. There is no configuration files or YAML or whatnot. You experiments written in Python, the development code in Python, the integration code in Python. This we think is like facilitate easy entrance for chemists to write experiments, and also kind of facilitate using the advances in AI and code generation. We built the system with data as the cornerstone of the system, where we realized that most of the experiments are run to generate data. So we built the system around kind of easy way to extract this data and use it around for like your AI or optimization or pipelines. And also, like, we wanted to pave the way towards like data standardization. Also, it was also built around microservices. This makes it very easy for us to extend the functionality of the system and integrate new stations and add new functionalities to it. Make the system decoupled, and also kind of would allow us to incorporate our previous workflows, and we can work concurrently on different components instead of focusing on one. So the architecture of Okra, in a nutshell, is basically we kind of have our lab and we have our lab users. Our chemists or lab users, they will interact with the system using pointer option later point. They will be using the Okra discovery package, which is a Python package that allow them to script their experiments, write them down, or the Okra web app, which is like a graphical user interface app that allow them to kind of monitor the experiments and control them. In the middle, we have the lab PC or the central server. This server basically manages all the data storage from the experiments and also the orchestration and sending the commands to the different stations we have around the lab, which brings me, our lab is basically divided into different stations, and a station can contain any number of devices or robots to control. They are they can be grouped in any way you want, but we kind of opted more to group them based on kind of physical location. So the station server will it will manage those devices, and it will handle the communication between them and the lab server. And then this is where we kind of like define the domain for our experts, where they can use this is where they can work to add drivers. So we abstracted and made it much easier to develop drivers and integrate them, and how to add stations, much more streamlined way of doing that. Just like before, it's we have a lab server that manages all the data and the communication and data handling between users and the stations. And the stations, basically, they are the ones that manages the low-level drivers and instruments that control all what you want to run. And our system, these servers can automatically register upon their start, so you don't have to run around, and if they shut down, they can re-register themselves, and if failure, they can restart themselves. So they have all this functionality to up and run. In Okra, basically, it's just to explain our devices. We have the device driver, which is the proprietary device that uses to communicate with robots and instruments. We create a device handler on top of it, which is a REST wrapper that allows to expose its functionality through the station server. And to order streamline how to add devices into our lab, we kind of came up with this kind of uniform or template to add it, where you have an abstract file that defines the data model for your device, any properties that have the device file, more like the science facing file that allows the science or the chemist to kind of to which functionalities they can use from that device or robot to interact with the system. And also we have the handler, which is more like the nitty-gritty that the engineer or the developer kind of writes, where he creates the core of that REST API wrapper that kind of exposes this functionality to the external world. The nice thing about this kind of structure, given with GitHub, we kind of tried to use GitHub Copilot to generate some devices given this template, so it managed to do it. So that's one of the nice things of this kind of templated approach. Next, I'll talk about how the experiments are programmed into our framework. So everything is written in Python. So that means you can use Python, all built-in function tools like loops, conditionals, whatnot. You can use it to write your experiments. You can also, since you're writing everything, you can import any library you want. So if you want to use the Bayesian optimization library or machine learning, you can just put it there. Also, this is all in Python, you can kind of use GitHub Copilot or any kind of code generation tool to write your experiments for you by just using a textual description. I mean, some of the limitations currently we have, all the operations in terms of transformation and material addition are explicitly defined. And in case of failure, we kind of work on a feature to resume where the failure happened. Just to go through data, so all executed operation and their result state on the database. Basic data types are stored directly on the database. Any complex data types such as LCMS results or images are all stored also on the database, and you can easily retrieve them within the code to access them directly. We have a generic database kind of handler that allow you to interact with any database you want. We implemented in Mongo, but you can try it to any database you want. And also, we already kind of have basic integration with like ELN, which we have like CipherMation within our lab. So that's kind of one of the like integration we started. And then in terms of like the web app, that provides a graphical user interface to see the station and devices and control them from anywhere you want, provided you control to the network. And also kind of like at the time when I left, we were building on a graphical interface to design experiments using drag and drop methodology. In conclusion, like building a self-driving lab is just connecting instruments, also require like a sophisticated orchestration layer that allow you to like write your experiments in a much more robust way to enable autonomous discovery. Yeah, acknowledgement to Adam Edwards, QIG, Bertie, and Professor Andy Cooper for like and for helping you with this work. Thank you very much.